Welcome to Sleepy Science Odyssey. Tonight, chaos theory. The mathematical framework revealing how deterministic systems can produce unpredictable behavior, from the discovery that tiny changes in initial conditions can lead to vastly different outcomes. The famous butterfly effect, to the intricate patterns called strange attractors that govern chaotic dynamics, from the self-similar structures of fractals appearing across scales in nature to the edge of chaos where complexity emerges. From weather systems and fluid turbulence to population dynamics and heartbeat rhythms. From Lorenz's computational accident that launched a revolution to the realization that chaos is not randomness, but deterministic unpredictability. From period-doubling roots to chaos to the universal constants governing transitions, from controlling chaos to harnessing it. We'll explore how simple rules can generate infinite complexity, how order and disorder intertwine, and how chaos theory transformed our understanding of prediction, determinism, and the nature of natural law. If you're new here, this channel is for people who need something to think about before they can stop thinking. Real mathematics and physics, no exaggeration, just quiet facts in the dark. Let's begin. Chaos theory studies dynamical systems that are highly sensitive to initial conditions, producing behavior that appears random despite being deterministic and governed by precise mathematical rules. The discovery of chaos revolutionized science by revealing that determinism does not imply predictability. For centuries, the Newtonian worldview held that if you knew the exact state of a system and the laws governing its evolution, you could predict its future indefinitely. The discovery of chaotic dynamics shattered this assumption. Even with perfect knowledge of laws and near-perfect knowledge of initial conditions, long-term prediction becomes impossible because arbitrarily small uncertainties grow exponentially over time. This sensitivity to initial conditions means that systems governed by simple, deterministic equations can produce behavior so complex that it appears random. The term chaos in scientific context differs from colloquial usage. In everyday language, chaos means complete disorder or randomness. In mathematics and physics, chaos refers to specific behavior in deterministic dynamical systems. Behavior that is aperiodic, meaning it never exactly repeats, bounded, meaning it doesn't fly off to infinity, and sensitive to initial conditions, meaning nearby trajectories diverge exponentially. Chaotic systems occupy a fascinating middle ground between perfect regularity and complete randomness, exhibiting patterns and structure despite apparent unpredictability. Henri Poincaré, working in the late 19th century on celestial mechanics, was perhaps the first to recognize what would later be called chaos. He studied the three-body problem, predicting the motion of three gravitating bodies, and discovered that the trajectories could be extraordinarily complex and sensitive to initial conditions. Poincaré realized that deterministic systems could produce unpredictable behavior, writing that it may happen that small differences in the initial conditions produce very great ones in the final phenomena. This insight went largely unappreciated for decades as mathematicians lacked tools to fully explore such systems. Edward Lorenz's 1963 discovery of chaos emerged from computational weather modeling. Lorenz created a simplified model of atmospheric convection using just three differential equations. One day, wanting to re-examine a particular simulation sequence, he restarted the computation from the middle using printed output values rounded to 3 decimal places instead of the computer's 6 decimal precision. To his surprise, the restarted simulation diverged dramatically from the original. This accident revealed extreme sensitivity to initial conditions. A difference of 1 part in 1,000 eventually produced completely different weather patterns. The Lorenz system consists of 3 coupled nonlinear differential equations. dx/dt equals sigma times the quantity y minus x, di/dt equals x times the quantity rho minus z minus y, and dz/dt equals xy minus beta times z. These equations were derived from simplified atmospheric convection equations, with x representing convection intensity, y representing horizontal temperature variation, and z representing vertical temperature variation. The parameters sigma, rho, and beta represent physical properties. For certain parameter values, particularly rho greater than approximately 24.7, the system exhibits chaotic behavior. When Lorenz plotted the system's trajectory in 3-dimensional phase space, a space where each axis represents one of the 3 variables, he discovered a remarkable structure now called the Lorenz attractor. The trajectory spirals around 2 lobes, occasionally switching between them in apparently random fashion, yet never exactly repeating and never settling into a periodic orbit. The attractor has intricate structure with nearby trajectories diverging exponentially while the overall shape remains bounded. This strange attractor became an icon of chaos theory. The butterfly effect, the popular term for sensitivity to initial conditions, derives from Lorenz's 1972 talk titled Predictability. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? The metaphor captures the idea that tiny perturbations can cascade through a chaotic system, ultimately producing large-scale effects. However, the butterfly effect is often misunderstood. It doesn't mean that butterflies cause tornadoes, but rather that in chaotic systems, arbitrarily small influences make long-term prediction impossible because you can never measure initial conditions with sufficient precision. Sensitive dependence on initial conditions can be quantified through Lyapunov exponents. The Lyapunov exponent measures the average exponential rate at which nearby trajectories diverge. For a one-dimensional map, if the distance between nearby points is delta 0 initially, after n iterations the distance becomes approximately delta 0 times e to the power of lambda times n, where lambda is the Lyapunov exponent. Positive Lyapunov exponents indicate chaos, trajectories diverge exponentially. Negative exponents indicate stability, trajectories converge. 0 exponents indicate neutral stability. The rate of divergence determines the prediction horizon, the time scale beyond which prediction becomes impossible. If the Lyapunov exponent is lambda and initial measurement uncertainty is epsilon, then accurate prediction is possible for time approximately 1 over lambda times the natural logarithm of 1 over epsilon. This shows that even with extremely precise initial measurements, the prediction horizon remains finite in chaotic systems. Weather forecasting illustrates this. Despite vast improvements in measurement and modeling, forecasts beyond approximately 2 weeks remain unreliable due to atmospheric chaos. Period doubling cascades provide one route from regular behavior to chaos. As a control parameter varies, a system may undergo a sequence of period doubling bifurcations. A period 1 orbit becomes unstable and is replaced by a period 2 orbit, which becomes unstable and is replaced by a period 4 orbit, which becomes period 8, 16, 32, and so on until the period becomes infinite and the motion becomes chaotic. This route to chaos was discovered independently by multiple researchers in different physical and biological systems. The logistic map, despite its simplicity, exhibits period doubling and chaos. The map is x next equals r times x times the quantity 1 minus x, where x represents population density between 0 and 1, and r is a growth parameter. For small r, populations die out. For r between 1 and 3, populations approach a stable equilibrium. As r increases beyond 3, the equilibrium becomes unstable and period doubling begins. Period 2 appears, then period 4, 8, 16, and so forth. By r approximately equal to 3.57, the cascade has accumulated and chaos emerges. For higher r values, chaotic regions alternate with periodic windows. Mitchell Feigenbaum discovered in 1975 that period doubling cascades share universal properties independent of specific system details. He found that the ratio of successive intervals between bifurcations approaches a constant delta approximately equal to 4.669201609. This Feigenbaum constant appears in every period doubling system, from fluid dynamics to population biology to electronic circuits, regardless of the specific equations. This universality revealed deep mathematical structure underlying roots to chaos. Feigenbaum also discovered a second universal constant alpha approximately equal to 2.5029, relating to spatial scaling at successive bifurcations. These universal constants suggest that period doubling systems belong to a universality class. Different systems share common behavior because they share common mathematical structure. This discovery connected chaos theory to statistical mechanics, where universality classes govern phase transitions. The universality of roots to chaos showed that despite apparently unlimited diversity, chaotic systems obey deep organizing principles. Bifurcation diagrams visualize how a system's long-term behavior changes as parameters vary. For the logistic map, plotting the parameter r horizontally and asymptotic values of x vertically produces a bifurcation diagram showing the period doubling cascade, chaotic regions appearing as dense clusters, and periodic windows appearing as distinct bands within chaos. The diagram reveals intricate structure, including self-similarity. Zooming into fine structure reveals patterns resembling the whole, a hallmark of fractals. Fractals are geometric objects exhibiting self-similarity across scales. The term fractal, coined by Benoit Mandelbrot in 1975, derives from the Latin fractus meaning broken or fragmented. Fractals have non-integer or fractal dimension. The Koch snowflake has dimension approximately 1.26, greater than a one-dimensional line, but less than a two-dimensional surface. Fractals appear throughout chaos theory. Strange attractors typically have fractal structure, and basin boundaries between different attractors are often fractal. The Mandelbrot set, perhaps the most famous fractal, is defined in the complex plane. For each complex number c, consider the iteration z next equals z squared plus c, starting from z equals 0. If the iteration remains bounded forever, c belongs to the Mandelbrot set. If it diverges to infinity, c is outside the set. The boundary of the Mandelbrot set has infinite complexity. Zooming reveals endless intricate detail, including miniature copies of the whole set. Though defined by a simple rule, the Mandelbrot set contains unlimited structure. The connection between the Mandelbrot set and the logistic map runs deep. There exists a correspondence between parameter values in the logistic map's bifurcation diagram and points in the Mandelbrot set. The main cardioid of the Mandelbrot set corresponds to stable fixed points in the logistic map. The circular bulb corresponds to period 2 orbits. Smaller bulbs correspond to higher period orbits. This correspondence reveals that the logistic map and complex dynamics share fundamental mathematical structure. The Cantor set illustrates fractal structure and self-similarity. Start with the interval from 0 to 1. Remove the middle third, leaving 2 intervals of length 1/3. From each remaining interval, remove the middle third. Continue indefinitely. The Cantor set consists of points remaining after infinite iterations. It has measure 0, total length 0, yet contains uncountably many points. Its fractal dimension is log 2 divided by log 3, approximately 0.63. The Cantor set structure appears in many chaotic systems, including basin boundaries. Strange attractors combine the boundedness of attractors with the fractal structure and sensitivity of chaos. Traditional attractors include fixed points where systems settle to constant values, limit cycles representing periodic oscillation, and tori representing quasi-periodic motion with multiple independent frequencies. Strange attractors differ. Trajectories neither settle to fixed values nor repeat periodically, yet remain bounded within a finite region. The attractor's geometry is fractal with non-integer dimension. The Lorenz attractor, Rössler attractor, and Heynon attractor exemplify strange attractors. The Rössler attractor, introduced by Otto Rössler in 1976, is simpler than the Lorenz attractor, yet exhibits similar chaotic behavior. The Rössler system consists of 3 equations: dx/dt equals negative y minus z, di/dt equals x plus I, dz/dt equals b plus z times the quantity x minus c for parameters a equals 0.2, b equals 0.2, c equals 5.7. The system produces a strange attractor resembling a folded band. Trajectories spiral outward, loop around, fold back, and repeat with sensitive dependence on initial conditions. The stretching and folding mechanism generates chaos in many systems. Stretching amplifies differences. Nearby points move apart, creating sensitivity to initial conditions. Folding brings distant points together, keeping trajectories bounded. Together, stretching and folding create strange attractors with fractal structure. Baker's transformation illustrates this. Imagine repeatedly stretching dough, folding it, and repeating. After many iterations, 2 initially nearby dough pieces become widely separated, while the overall shape remains bounded. This simple mechanical process captures the essence of chaos. Poincaré sections reduce continuous dynamical systems to discrete maps, simplifying analysis. For a 3-dimensional flow, define a 2-dimensional surface transverse to the flow. Plot points where trajectories pierce this surface. For periodic orbits, the Poincaré section shows fixed points or periodic points. For strange attractors, the section reveals fractal structure. Successive piercings trace complex, non-repeating patterns. Poincaré sections transform flows into maps while preserving dynamical properties, including chaos. Symbolic dynamics provides another approach to analyzing chaos. Partition phase space into regions and assign symbols to regions. A trajectory generates a sequence of symbols as it moves between regions. For chaotic systems, allowed symbol sequences obey grammatical rules. Certain sequences are forbidden by dynamics. Symbolic dynamics connects chaos to information theory and computation. Chaotic systems can be viewed as computers generating symbol sequences, with entropy production measuring information creation rate. Topological entropy quantifies chaos by measuring exponential growth of distinguishable trajectories. For symbolic dynamics with n⁻n distinguishable trajectories of length n, topological entropy equals the limit as n approaches infinity of log n⁻n divided by n positive topological entropy indicates chaos. Zero entropy indicates regular motion. Like Lyapunov exponents, topological entropy provides a rigorous chaos criterion, though it's often harder to compute than Lyapunov exponents. Ergodicity connects time averages and space averages in dynamical systems. An ergodic system has the property that time averages along almost every trajectory equal space averages over the entire phase space. For ergodic chaotic systems, a single long trajectory eventually visits every region of phase space with frequency proportional to region size. This means observing one trajectory for long time provides the same statistics as observing many trajectories simultaneously, a powerful property for understanding chaotic systems. Mixing is stronger than ergodicity. A mixing system has the property that any region of phase space eventually spreads throughout the accessible space. For mixing systems, knowing the past provides no information about the future beyond statistical properties. Chaotic systems are typically mixing, though mixing doesn't require chaos. Mixing implies ergodicity, but not vice versa. The distinctions between regular, ergodic non-chaotic, and chaotic mixing systems clarify the hierarchy of dynamical complexity. Quasi-periodicity represents motion on tori in phase space with multiple incommensurate frequencies. A two-frequency quasi-periodic system traces a path on a torus, winding around both toroidal and poloidal directions. If frequency ratio is irrational, the path never exactly repeats, but densely fills the torus surface. Quasi-periodic motion is predictable. Knowing initial conditions allows predicting future positions arbitrarily far ahead. The KAM theorem describes how quasi-periodic tori break down under perturbation, sometimes giving way to chaos. The KAM theorem, named for Kolmogorov, Arnold, and Moser, addresses perturbations of integrable systems. Unperturbed integrable systems have motion confined to tori. Small perturbations destroy some tori while others persist. Tori corresponding to sufficiently irrational frequency ratios survive perturbation. They are robust. Tori with rational frequency ratios or poorly irrational ratios break up, creating chaotic regions. The KAM theorem explains why solar system remains stable despite small planetary perturbations, while three-body systems can be chaotic. Hamiltonian systems, describing conservative mechanical systems where energy is conserved, exhibit distinctive chaos features. Hamiltonian chaos preserves phase space volume, Liouville's theorem, preventing the attractors found in dissipative systems. Hamiltonian systems have zero average Lyapunov exponents. If one direction shows exponential divergence, another shows exponential convergence. Hamiltonian chaos appears in celestial mechanics, particle accelerators, and plasma physics. The interplay of chaotic and regular regions in Hamiltonian systems creates intricate phase space structure. Dissipative systems, where energy dissipates over time, allow attractors, including strange attractors. The Lorentz system is dissipative. Phase space volume contracts exponentially, with all trajectories eventually confined to the attractor's zero-volume structure. Most real-world systems are dissipative due to friction and other energy loss mechanisms. Dissipative chaos is easier to observe experimentally than Hamiltonian chaos because systems relax onto attractors that can be characterized through extended observation. The transition to turbulence in fluid flow involves chaos. Laminar flow is smooth and predictable. As flow velocity increases, the Reynolds number ratio of inertial to viscous forces increases. Beyond critical Reynolds numbers, flow becomes turbulent, irregular, unpredictable, containing eddies across multiple scales. The Rule-Taken scenario proposes that turbulence emerges through a sequence of bifurcations, creating strange attractors. While fully developed turbulence involves many degrees of freedom beyond low-dimensional chaos, chaotic dynamics contributes to turbulence onset. The Navier-Stokes equations governing fluid flow are deterministic partial differential equations, yet they produce turbulence that appears random. This exemplifies how deterministic equations can generate apparent randomness through chaos. Whether Navier-Stokes solutions remain smooth for all time or develop singularities remains an unsolved millennium problem in mathematics. Understanding turbulence through chaos theory remains an active research area with applications from aerodynamics to climate. Chaos appears in diverse natural phenomena from weather and climate to biology, revealing universal patterns across scientific disciplines. Chaos theory transformed from mathematical curiosity to scientific revolution as researchers discovered chaotic dynamics throughout nature. Systems as different as weather, wildlife populations, heartbeats, and planetary orbits exhibit chaos, revealing that this behavior is not exceptional but ubiquitous. The discovery of chaos in so many contexts showed that determinism does not guarantee predictability, and that nature operates closer to the edge of chaos than previously imagined. Weather systems provided the original context for chaos discovery through Lorenz's work. The atmosphere is a fluid system governed by Navier-Stokes equations, conservation laws, and thermodynamics. Atmospheric flow exhibits sensitivity to initial conditions, making long-range weather prediction fundamentally limited. Modern weather forecasting combines vast data collection, supercomputer simulations, and ensemble forecasting, running multiple simulations with slightly perturbed initial conditions to estimate prediction uncertainty. Despite technology advances, the 2-week forecast horizon remains difficult to extend due to atmospheric chaos. Climate differs from weather. Weather is short-term atmospheric state, while climate is long-term statistics. Though individual weather events are chaotic and unpredictable, climate statistics might be more predictable. However, climate systems also exhibit complex dynamics, potentially including chaos. Paleoclimate records show abrupt climate changes, suggesting nonlinear threshold behavior. Interactions between atmosphere, oceans, ice sheets, and biosphere create coupled nonlinear systems that can exhibit chaotic dynamics, regime shifts, and tipping points. Ocean circulation patterns exhibit complex dynamics and potential chaos. The thermohaline circulation, or global conveyor belt, transports heat through ocean basins, driven by temperature and salinity gradients. Models suggest this circulation could have multiple stable states or exhibit chaotic transitions. Past abrupt climate changes, like Younger Dryas cooling 12,000 years ago, may have resulted from ocean circulation changes. Understanding whether ocean circulation exhibits deterministic chaos has implications for predicting future climate changes. Population dynamics in ecology show chaotic behavior in models and some natural populations. The logistic map was originally introduced as a population model. X represents population density, and R represents growth rate. Natural populations with discrete generations and strong density dependence can exhibit period doubling and chaos. Flower beetles in laboratory experiments show population fluctuations matching chaotic dynamics predictions. Whether natural populations commonly exhibit chaos remains debated. Environmental stochasticity complicates distinguishing chaos from randomness. Predator-prey dynamics can be chaotic. The Lotka-Volterra equations produce periodic oscillations in prey and predator numbers. Adding realistic complications like prey refuges, age structure, or spatial structure can produce chaotic dynamics. Time series from Canadian lynx and snowshoe hare populations show irregular fluctuations that might reflect chaotic dynamics, though separating chaos from environmental noise and sampling errors remains challenging. Chaos in predator-prey systems could stabilize coexistence or contribute to extinction. Epidemics and disease dynamics exhibit complex temporal patterns, including chaos. Models of childhood diseases like measles, chickenpox, and rubella show that transmission rates, seasonal forcing, and population structure can produce chaotic dynamics. Historical measles data shows irregular cycles, potentially reflecting deterministic chaos. Understanding disease dynamics helps predict outbreaks and design vaccination strategies. Distinguishing chaotic dynamics from stochastic fluctuations in epidemiological data requires careful statistical analysis. Cardiac rhythms can exhibit chaotic dynamics with implications for health and disease. Healthy heartbeat variability shows complex irregular fluctuations, suggesting chaotic dynamics. Hearts operating near the edge of chaos have maximal adaptability. Loss of complexity and variability associates with disease and aging. Conversely, pathological heart rhythms, including fibrillation, involve high-dimensional chaos where normal coordinated contraction breaks down. Understanding cardiac chaos could enable better monitoring and intervention for heart disease. Neural dynamics exhibits chaos at multiple scales. Individual neurons can fire chaotically under certain conditions. Neural networks with recurrent connections and nonlinear activation functions can produce chaotic activity. Electroencephalogram, or EEG recordings, show irregular patterns potentially reflecting cortical chaos. Some theories propose that brain operates at the edge of chaos, balancing stability and flexibility. Chaotic dynamics might enable rapid switching between different activity patterns, supporting cognitive flexibility. The olfactory system in insects and other animals appears to use chaotic dynamics for odor processing. Locust antennal lobe neurons exhibit chaotic activity in absence of odors. Odor presentation transiently quenches chaos, producing brief stereotyped responses before returning to chaos. This transition from chaos to order and back might enable rapid odor recognition and clearing of previous odor information. Using chaos for computation represents a novel principle distinct from traditional neural network models. Chemical reactions can exhibit chaotic oscillations. The Belousov-Zhabotinsky reaction, involving bromate oxidation of malonic acid catalyzed by cerium ions, produces temporal oscillations and spatial patterns. Under some conditions, oscillations become chaotic. The reaction produces visible color changes as cerium ions switch between oxidation states, allowing direct observation of chemical chaos. This reaction demonstrated that chemical systems far from equilibrium can exhibit complex dynamics, including chaos. The three-body problem in celestial mechanics exhibits chaos for most initial conditions. Unlike the two-body problem with its stable elliptical orbits, Three gravitating bodies generally produce chaotic motion. Planetary systems with multiple planets can be chaotic, though our solar system shows relative stability over billion-year time scales due to particular orbital configurations. Some exoplanetary systems likely experience stronger chaos, possibly leading to planet ejection or collisions. Asteroid orbits can be chaotic due to gravitational perturbations from planets, particularly Jupiter. Some asteroids occupy chaotic orbits with Lyapunov times, time scales for predictability loss, of tens to hundreds of years. This chaos makes long-term prediction of asteroid positions impossible, with implications for both understanding solar system evolution and predicting potential Earth impacts. Chaotic evolution can pump asteroids into Earth-crossing orbits over million-year time scales. Planetary spin axis orientation can be chaotic. Mars shows chaotic obliquity variations. Axial tilt changes irregularly over millions of years due to gravitational torques from other planets and Mars's moons. These obliquity changes affect climate dramatically. Earth's obliquity is stabilized by the moon's gravitational influence. Without the moon, Earth's obliquity would vary chaotically, producing extreme climate variations. This suggests that large moons might be important for planetary habitability. Saturn's moon Hyperion exhibits chaotic rotation. Most moons are tidally locked, keeping one face toward their planet. Hyperion's irregular shape and eccentric orbit prevent tidal locking, resulting in chaotic tumbling, its rotation axis, and rate very unpredictably. Observations show Hyperion spinning and tumbling erratically, making its rotational state unpredictable beyond weeks, despite simple gravitational laws governing its motion. This demonstrates chaos in a directly observable astronomical system. Plate tectonics shows complex spatio-temporal patterns, possibly involving chaos. The pattern of plates, their sizes, motions, and evolution over Earth's history appears irregular. Models suggest plate dynamics could be chaotic, with small perturbations affecting long-term evolution. The timing of supercontinent assembly and breakup, changes in plate configuration, and volcanic activity patterns might reflect underlying chaotic dynamics in mantle convection, driving plate motion. Earthquakes exhibit complex irregular patterns that might involve chaos. Earthquake timing and magnitudes follow statistical distributions, but whether underlying dynamics are chaotic, self-organized critical, or stochastic remains debated. Some models produce earthquake-like behavior through deterministic chaos in fault stick-slip dynamics. Distinguishing these scenarios from observational data is challenging. Understanding earthquake dynamics is crucial for hazard assessment, though earthquake prediction remains elusive partly because potential chaotic dynamics limit predictability. Climate oscillations like El Niño Southern Oscillation, or ENSO, show irregular patterns that might reflect chaos. ENSO involves coupled atmosphero-ocean dynamics in the tropical Pacific, producing warm El Niño and cool La Niña conditions with global climate impacts. ENSO events occur every 2 to 7 years with irregular timing and intensity. Models suggest ENSO dynamics might be chaotic, though stochastic forcing from weather also contributes. Predicting ENSO beyond approximately 6 months remains challenging. Solar magnetic activity, including sunspots and solar flares, exhibits irregular 11-year cycles with chaotic fluctuations. Sunspot numbers vary quasi-periodically, but with irregular amplitude and timing variations. The solar dynamo generating magnetic fields involves complex fluid dynamics potentially exhibiting chaos. Solar activity affects space weather, satellite operations, and possibly Earth's climate. Understanding solar magnetic dynamics through chaos theory could improve space weather prediction. Economic systems exhibit irregular fluctuations that might involve chaotic dynamics. Economic variables like prices, production, and employment show complex temporal patterns. Some economic models produce chaotic dynamics from interactions between consumers, producers, and markets. Whether real economic data contains signatures of deterministic chaos remains controversial. Distinguishing chaos from stochastic fluctuations and high-dimensional dynamics is challenging with limited noisy data. Chaos could contribute to economic cycles and financial crashes. Stock market dynamics shows complex irregular fluctuations with occasional crashes. Some researchers propose that market dynamics are chaotic, driven by nonlinear feedback between prices and investor behavior. However, efficient market hypothesis suggests prices follow random walks. Distinguishing these scenarios is difficult. Regardless of whether markets are truly chaotic, nonlinear dynamics and feedback clearly play important roles. Understanding these dynamics has practical importance for trading, risk management, and regulation. Dripping faucets provide an accessible chaotic system. At low flow rates, drops fall periodically with regular intervals. As flow increases, period doubling occurs, pairs of drops fall with alternating intervals. Further increasing flow produces period 4, period 8, and eventually chaotic dripping with irregular intervals. This simple system demonstrates period doubling routes to chaos in a kitchen experiment. High-speed video reveals complex drop formation dynamics underlying the apparently simple drip. The double pendulum, a pendulum suspended from another pendulum, exhibits spectacular chaos. For small oscillations, motion is regular and predictable. For large initial displacements, motion becomes chaotic with sensitive dependence on initial conditions. The double pendulum swings, rotates, and flips in apparently random fashion, never repeating patterns. Despite being governed by deterministic mechanics, long-term prediction is impossible. The double pendulum provides a dramatic demonstration of chaos emerging from simple Newtonian mechanics. Magnetic pendulums exhibit chaos when multiple magnets influence a magnetized pendulum. The pendulum swings above an array of magnets, with its motion determined by gravitational and magnetic forces. Depending on initial conditions, the pendulum eventually settles above different magnets. Basin boundaries between different final states have fractal structure. Nearby starting points can lead to different outcomes. This system demonstrates fractal basin boundaries and sensitive dependence in a simple physical system. Laser dynamics can exhibit chaos due to nonlinear interactions between light, atoms, and cavity mirrors. Laser intensity can show periodic pulsing, period doubling, and chaotic fluctuations depending on parameters like pump power and cavity detuning. Chaotic lasers have applications in secure communications. Chaotic output appears random and unpredictable, providing encryption. Two synchronized chaotic lasers can communicate while resisting eavesdropping. Laser chaos also appears as unwanted instability requiring control. Electronic circuits provide controllable chaotic systems for research. The Chua circuit, consisting of resistors, capacitors, inductors, and a nonlinear element, produces chaotic oscillations. The circuit's simplicity makes it ideal for experimental studies and teaching. Many chaos theory concepts, including strange attractors, bifurcations, and sensitivity, can be demonstrated with electronic circuits. Circuits also enable testing chaos control methods and chaotic communications schemes. Chaos in engineering systems is sometimes useful and sometimes problematic. Chaotic mixing in fluids enhances mixing efficiency for chemical reactors and microfluidics. Chaotic vibrations in cutting tools can improve surface finish in machining. Conversely, chaos appears as unwanted instabilities in power grids, aircraft flutter, and structural vibrations. Understanding and controlling chaos is important across engineering disciplines. The engineering question is often not whether systems are chaotic, but how to exploit or suppress chaos as needed. Mathematical tools and techniques allow characterizing, quantifying, and understanding chaotic systems. Analyzing chaotic systems requires mathematical machinery beyond standard calculus and linear algebra. Because chaos involves long-term irregular behavior and fractal structure, new tools were developed for measuring dimension, quantifying unpredictability, and extracting structure from complexity. These techniques transformed chaos from a qualitative observation to a quantitative science with rigorous definitions, theorems, and computational methods. Fractal dimension quantifies space-filling properties of sets and provides a measure of strange attractor complexity. Several dimension definitions exist. The box counting dimension divides space into boxes of size epsilon and counts n epsilon, the number of boxes containing attractor points. The box counting dimension equals the limit as epsilon approaches 0 of log n epsilon divided by log 1 over epsilon. For simple objects, a point has dimension 0, a line has dimension 1, a plane has dimension 2. Strange attractors have non-integer dimension, reflecting fractal structure. The correlation dimension provides an alternative fractal dimension measure, particularly useful for experimental data. For a set of points on an attractor, count the number of point pairs with separation less than r. The correlation integral C of r measures this number as a function of r for an attractor with dimension d. C of r scales as r to the d power for small r. So d equals the slope of log C of r versus log r. The correlation dimension can be estimated from time series data, enabling dimension estimation from experimental measurements. Lyapunov exponents quantify sensitive dependence on initial conditions. For an n-dimensional system, there are n Lyapunov exponents corresponding to n phase space directions. The largest Lyapunov exponent lambda1 determines overall predictability. Positive lambda1 indicates chaos with prediction horizon proportional to 1 over lambda1. The sum of Lyapunov exponents determines whether phase space volume expands, contracts, or is conserved. For dissipative systems, the sum is negative. For Hamiltonian systems, the sum is 0. Computing Lyapunov exponents from equations involves linearizing dynamics around trajectories. For a map x next equals f of x, the linearization at x is the Jacobian matrix df of x. The Lyapunov exponents equal logarithms of eigenvalues of the matrix M equals the limit as n approaches infinity of the product of Jacobians along the trajectory to the power of 1 over n in practice. QR decomposition or other numerical methods prevent overflow from exponentially growing products. Computing Lyapunov exponents from data requires reconstructing the attractor and estimating local divergence rates. Taken's embedding theorem shows that chaotic attractors can be reconstructed from scalar time series. Given measurements of a single variable x at discrete times, form delay vectors of the form x of t plus tau, x of t plus 2 tau, x of t plus m minus 1 tau, where tau is time delay and m is embedding dimension. Takens proved that for sufficiently large m, these delay vectors faithfully reconstruct the attractors topology. This theorem enables analyzing experimental systems where only one variable is measured. Choosing appropriate time delay tau and embedding dimension m is crucial for embedding. If tau is too small, coordinates are redundant, successive values are nearly identical. If tau is too large, coordinates are independent, successive values are uncorrelated. Common methods for choosing tau include using the first minimum of the autocorrelation function or the first minimum of the mutual information. Embedding dimension, m must exceed twice the attractor dimension. False nearest neighbors methods determine sufficient m by checking when apparent neighbors are genuinely close in higher dimensions. Recurrence plots visualize time series structure. For each time pair I and j, mark a point if the distance between x of ti and x of tj is below a threshold. The resulting plot shows when the system revisits similar states. Periodic systems show diagonal stripes. Chaotic systems show short diagonal segments reflecting approximate recurrences. Recurrence quantification analysis extracts statistics from recurrence plots including determinism, laminarity, and entropy, characterizing system dynamics from time series. Power spectra reveal frequency content of time series. For periodic systems, power spectra show discrete peaks at fundamental frequency and harmonics. For quasi-periodic systems, spectra show multiple incommensurate peaks. For chaotic systems, spectra show broadband continuous components rather than discrete peaks. Chaos produces all frequencies. Computing power spectra through Fourier transforms is a standard analysis method for distinguishing periodic, quasi-periodic, and chaotic dynamics from time series data. Phase space reconstruction from time series enables geometric analysis of attractors. Once an attractor is reconstructed through embedding, geometric properties can be computed. Correlation dimension, Lyapunov exponents, and recurrence properties can all be estimated from reconstructed attractors. This allows characterizing experimental systems without knowing governing equations. Numerous systems have been analyzed this way, including measles epidemics, cardiac rhythms, fluid convection, and laser oscillations. Surrogate data testing addresses whether observed irregularity reflects deterministic chaos or stochastic noise. Generate surrogate datasets with the same power spectrum and distribution as the original data, but lacking deterministic structure. If test statistics like correlation dimension or Lyapunov exponents differ significantly between original and surrogate data, this suggests deterministic structure. Surrogate testing provides statistical evidence for chaos rather than merely fitting chaotic models to potentially random data. The Poincaré map, or first return map, simplifies continuous flows to discrete maps. For a flow in n-dimensional phase space, define an n-1 dimensional surface transverse to the flow. Plot successive intersections with this surface. For periodic orbits, the Poincaré map shows fixed points. For chaotic attractors, the map reveals intricate structure. The Poincaré map reduces dimensions while preserving dynamical properties, enabling visualization and analysis of high-dimensional systems. Symbolic dynamics partitions phase space and assigns symbols to regions. Trajectories generate symbol sequences as they visit different regions. For the logistic map, partition the interval at the maximum. Symbol 0 represents iterates in the left partition, symbol 1 represents the right partition. Orbits generate binary sequences. Certain sequences are forbidden by dynamics. For example, if the map is decreasing on one partition, certain symbol transitions cannot occur. Symbolic dynamics connects chaos to formal language theory and computation. The shadowing lemma states that for hyperbolic chaotic systems, numerical trajectories with small errors are shadowed by true trajectories. There exists a true trajectory staying close to the numerical trajectory. This surprising result means that despite exponential divergence and rounding errors, numerical simulations of chaotic systems are meaningful. Computed trajectories don't represent the intended initial condition, but do represent nearby initial conditions. Shadowing validates numerical chaos studies despite inevitably imperfect computation. Hyperbolic systems represent well-understood chaos. A hyperbolic system has the property that at each attractor point, tangent space divides into stable and unstable directions. Small perturbations in stable directions decay exponentially, while perturbations in unstable directions grow exponentially. Hyperbolic systems satisfy rigorous mathematical theorems, including the shadowing lemma, and have well-defined fractal dimensions and Lyapunov exponents. Many physical systems are hyperbolic or nearly so. Non-hyperbolic chaos is less well understood mathematically. Some chaotic systems contain regions where stable and unstable directions are not clearly separated, tangent directions that are neither expanding nor contracting. The Lorenz attractor contains such non-hyperbolic regions. Non-hyperbolic systems can exhibit intermittency, irregular alternation between chaotic and nearly regular behavior. Mathematical analysis is more difficult for non-hyperbolic systems, and some properties are less robust. Intermittency describes irregular switching between different behaviors. Type 1 intermittency involves alternation between periodic and chaotic behavior. The system spends time near an unstable periodic orbit before bursting into chaotic motion. Type 3 intermittency involves intermittent bursts in otherwise regular behavior. Intermittency appears in many systems, including fluid turbulence and chemical reactions. Characterizing intermittency requires statistics of burst durations and distributions. The spectrum of singularities, or multifractal analysis, characterizes heterogeneous attractor structure. Strange attractors often have non-uniform invariant measures. Some regions are visited more frequently than others. Multifractal analysis characterizes this inhomogeneity through a spectrum of dimensions rather than a single fractal dimension. The F-alpha spectrum plots the dimension f of alpha versus the Hölder exponent alpha, revealing the distribution of local scaling properties across the attractor. Entropies quantify information production or loss in dynamical systems. The Kolmogorov-Sinai entropy measures the rate at which system generates new information. How much the future is uncertain given the past. For chaotic systems, entropy is positive. The system produces information. For regular systems, entropy is zero. Kolmogorov-Sinai entropy equals the sum of positive Lyapunov exponents, connecting information theory and dynamics. Entropy provides another chaos criterion beyond Lyapunov exponents. Partitioning algorithms divide phase space to analyze symbolic dynamics. Generating partitions creates symbols that uniquely identify trajectories. Knowing the infinite symbol sequence determines the initial condition. Generating partitions exist for hyperbolic systems. Finding good partitions for non-hyperbolic systems is difficult. Optimal partitioning maximizes information extraction while minimizing partition complexity. Partition refinement methods iteratively improve partitions based on dynamical structure. Wavelet analysis decomposes signals into time-frequency components, providing advantages over Fourier analysis for non-stationary signals. Wavelets are localized in both time and frequency, allowing identification of transient features. For chaotic systems with varying dynamics, wavelets reveal temporal structure that Fourier analysis misses. Continuous wavelet transforms show how frequency content evolves over time. Discrete wavelet transforms enable multi-resolution analysis, exposing structure at multiple scales. Coherent structures in spatially extended chaotic systems represent organized patterns emerging from chaos. In turbulent flows, coherent structures are vortices and other features persisting longer than typical turbulent time scales. Identifying coherent structures requires methods like proper orthogonal decomposition or dynamic mode decomposition that extract dominant patterns from high-dimensional data. Understanding coherent structures helps predict turbulence behavior and control fluid flow. Network analysis applies to spatiotemporal chaos. Divide a spatially extended system into nodes and define edges based on correlations or causal influences. The resulting network captures how different spatial regions interact. Network properties like clustering, modularity, and centrality reveal organizational principles. Network analysis has been applied to climate systems, neural dynamics, and power grids, revealing how local chaos couples across space. Machine learning offers new tools for analyzing chaotic systems. Neural networks can predict chaotic time series for short horizons, learning complex dynamics from data. Reservoir computing uses recurrent neural networks for chaotic time series prediction. Autoencoders discover low-dimensional representations of high-dimensional chaotic data. Physics-informed neural networks incorporate known dynamical equations while learning unknown components. Machine learning complements traditional chaos analysis, especially for complex real-world systems. Controlling chaos and exploiting chaotic dynamics enable practical applications across science and engineering. Initially seen as a fundamental limit to prediction and control, chaos is now recognized as offering opportunities. Chaotic systems can be controlled with surprisingly small perturbations, exploiting sensitivity to redirect trajectories toward desired behaviors. Chaos can be intentionally generated for beneficial purposes, including mixing, encryption, and optimization. Understanding chaos enables designing systems that avoid unwanted chaos or harness chaos for useful functions. The OGY method, named for Ott, Grebogi, and York, who developed it in 1990, enables chaos control with minimal intervention. Chaotic attractors typically contain infinitely many unstable periodic orbits, periodic solutions that would persist if stabilized, but are unstable in the chaotic state. The OGY method identifies these orbits and applies small perturbations to stabilize them. By adjusting an accessible parameter slightly at each iteration, the system is kept near the desired periodic orbit. The required perturbations are small because of sensitivity to initial conditions. Targeting in chaotic systems enables reaching desired states faster than random wandering. Because chaotic trajectories ergodically explore the attractor, the system eventually approaches any desired state. Targeting uses small perturbations to guide the trajectory to the desired region more quickly. Applications include spacecraft orbit transfers using gravitational assists. Chaos in the three-body problem allows fuel-efficient orbital maneuvers by following chaotic separatrix regions where small velocity changes produce large orbital changes. Synchronization of chaotic systems occurs when two or more chaotic systems evolve in coordinated fashion despite chaos. Complete synchronization occurs when systems follow identical trajectories. Generalized synchronization occurs when a functional relationship exists between system states, even if not identical. Phase synchronization occurs when phases lock while amplitudes remain uncorrelated. Chaos synchronization enabled applications including secure communications and network coordination. Chaotic cryptography exploits sensitive dependence for encryption. The sender and receiver each have identical chaotic systems. A message modulates the sender's system, producing a chaotic signal. The receiver system synchronizes with the sender, enabling message extraction. Eavesdroppers cannot decrypt without knowing system parameters and initial conditions. Though vulnerabilities exist, chaotic cryptography offers an alternative to traditional encryption based on computational difficulty. Chaotic communications embed information in chaotic carriers. In chaos shift keying, different chaotic attractors represent different symbols. Switching between attractors encodes digital data. In chaos masking, the message is added to a chaotic signal, with chaos obscuring the message. In chaos modulation, the message modulates a parameter of a chaotic system. The receiver's synchronized chaotic system recovers the message. These methods exploit chaos for spread spectrum communications resistant to jamming and interception. Chaotic mixing enhances mixing in fluids and granular materials. Laminar flow produces poor mixing. Fluid elements follow regular paths with limited intermingling. Introducing chaos through time-varying flows or complex geometry stretches and folds fluid elements, rapidly generating fine-scale structures. Applications include microfluidic devices where turbulence is impossible due to low Reynolds numbers, chemical reactors where efficient mixing improves reactions, and mixing dough and other materials. The double-scroll attractor, generated by Chua's circuit, demonstrates how simple circuits produce complex chaos. The circuit contains resistors, capacitors, inductors, and a nonlinear resistor with piecewise linear voltage-current relationship. The resulting dynamics produces a double-lobed attractor similar to the Lorenz attractor, but in a simple electronic circuit. Chua's circuit has become a standard experimental platform for chaos research and engineering applications. Chaos in optimization algorithms helps escape local minima. Simulated annealing uses random perturbations analogous to thermal fluctuations for optimization. Chaotic optimization replaces random noise with chaotic dynamics, providing deterministic perturbations that systematically explore solution space. The ergodic property ensures all regions are visited. Chaotic search can outperform random search for certain optimization problems, particularly those with many local minima. Neural networks with chaotic dynamics might enhance computational capabilities. Transient chaos allows rapid switching between different attractors representing different memories or computations. Edge of chaos operation balances stability and flexibility. Some researchers propose that brain operates near criticality, the boundary between order and chaos, optimizing information processing, storage capacity, and computational power. Whether real neural networks exploit chaos remains debated, but represents an intriguing possibility. Chaotic itinerancy describes dynamics transitating among different quasi-stable states. Unlike settling to an attractor, the system visits a sequence of states, remaining in each for variable durations before switching. This behavior appears in neural networks and possibly brain dynamics. Chaotic itinerancy might enable flexible cognition, rapid switching between thoughts and percepts. Mathematical models produce chaotic itinerancy through weakly coupled chaotic elements. Controlling spatio-temporal chaos in extended systems poses additional challenges. Spatially extended systems like chemical reactions, fluid flow, or coupled oscillators produce complex spatial patterns evolving chaotically. Controlling such systems requires sensing and actuating at multiple spatial locations. Techniques include global feedback acting on spatial averages, local feedback at selected positions, and pinning control that stabilizes key spatial features. Applications include suppressing turbulence and controlling pattern formation. Time-delayed feedback control uses past states to stabilize periodic orbits. The Paragas method feeds back the difference between current and delayed states, providing self-controlling feedback without needing to know the unstable periodic orbit explicitly. The delay is chosen to match the period of the desired orbit. This method is non-invasive. When the orbit is stabilized, feedback vanishes. Time-delayed feedback has been applied to lasers, chemical reactions, and electronic circuits. Anti-control of chaos involves intentionally creating or enhancing chaos. Some applications benefit from chaos, mixing, encryption, and exploration. Anti-control methods make stable systems chaotic by adjusting parameters, adding feedback, or introducing delays. Chaos can also be enhanced by increasing Lyapunov exponents or expanding attractor dimensions. Designing systems that are chaotic on demand provides engineering flexibility. Chaotic resonance occurs when chaotic dynamics enhance response to weak signals. In stochastic resonance, noise enhances signal detection in nonlinear systems. Chaotic resonance similarly uses deterministic chaos instead of stochastic noise. The irregular dynamics provide a mechanism for amplifying weak periodic inputs. Potential applications include signal detection, energy harvesting, and neural information processing. Basin boundary crossing enables controlling which attractor a system approaches. When multiple attractors coexist, initial conditions determine final states. Basins of attraction have fractal boundaries in chaotic systems. Small perturbations can switch between basins. Applying small targeted perturbations causes basin boundary crossing, allowing selection of desired attractors. This is useful for switching between operational modes in multi-stable systems. Adaptive control of chaos adjusts control parameters online based on system response. Fixed parameter control might fail if system properties drift or face external perturbations. Adaptive control updates parameters to maintain desired behavior despite changes. Methods include model reference adaptive control matching system behavior to a desired model, and self-tuning control that estimates system properties and adjusts control accordingly. Adaptive chaos control is important for real-world applications where conditions vary. Chaos-based random number generation exploits chaos for producing pseudorandom numbers. True random number generators use physical noise sources, while pseudorandom generators use algorithms. Chaotic systems produce deterministic sequences with statistical properties resembling random numbers. Chaotic maps like the logistic map or tent map generate number sequences that pass randomness tests. Advantages include speed and reproducibility. Same initial conditions produce same sequence for testing and verification. The edge of chaos and complexity theory explore how order and chaos interact to generate complex behavior and adaptive systems. Between rigid order and formless chaos lies an intermediate regime where the most interesting dynamics occur, the edge of chaos. This region combines stability and flexibility, allowing systems to compute, adapt, and evolve. Complex adaptive systems from biological evolution to economies might operate near this critical boundary, suggesting that the edge of chaos is not just a mathematical curiosity, but a fundamental principle of natural organization. Cellular automata illustrate how simple rules generate complex patterns. A cellular automaton consists of a grid of cells, each in a discrete state. All cells update synchronously based on local rules, depending on cell and neighbor states. Stephen Wolfram studied elementary cellular automata, one-dimensional arrays with binary states and rules depending on cell and two neighbors. Despite simplicity, some rules produce complex behavior, including propagating structures, intricate patterns, and chaos. Wolfram classified cellular automata into 4 classes. Class 1 systems evolve to homogeneous states. All cells become identical. Class 2 systems produce stable or periodic structures. Class 3 systems produce chaotic aperiodic patterns. Class 4 systems produce complex localized structures that interact in intricate ways, the edge of chaos. Class 4 automata include Rule 110, which produces complex patterns supporting universal computation. Rule 110 is universal, capable of emulating any computation. This demonstrates that simple rules can support arbitrary complexity and computation. Universal computation emerges at the edge of chaos, where structures are stable enough to persist, yet flexible enough to interact productively. This suggests computational capability requires balancing order and chaos. Too much order prevents complex information processing. Too much chaos prevents reliable computation. The game of life, invented by John Conway, is a two-dimensional cellular automaton exhibiting rich phenomenology. Cells are alive or dead. Live cells with 2 or 3 live neighbors survive. Dead cells with 3 live neighbors become alive. All other cells die. These simple rules produce gliders, patterns that move across the grid, glider guns, structures that emit streams of gliders, and infinitely many other structures. Life is universal, supporting computation through interacting gliders. Self-organized criticality, or SOCH, describes systems that naturally evolve toward critical states without external tuning. The sandpile model illustrates SOCH. Sand grains are dropped onto a pile. When the slope becomes too steep, avalanches occur. The system self-organizes to a critical slope where avalanches of all sizes occur following power law distributions. SOCH systems exhibit scale-free dynamics, no characteristic size for events. Examples might include earthquakes, forest fires, and extinction events. Power law distributions characterize SOCH and critical systems. Instead of exponential or Gaussian distributions with characteristic scales, power laws follow P of x proportional to x to the minus alpha, where events of all sizes occur with frequencies related by the exponent alpha. Power laws indicate scale invariance. The system looks similar at all scales. Identifying power laws in data suggests criticality or self-organization, though distinguishing power laws from other heavy-tailed distributions requires careful analysis. The criticality hypothesis proposes that brain operates near a critical point between order and disorder. Neural activity shows avalanche dynamics following power laws, suggesting criticality. Operating at criticality maximizes information transmission, dynamic range, and computational capability. Subcritical networks have insufficient activity for flexible computation. Supercritical networks have excessive activity, preventing stable information storage. Critical networks balance these extremes, optimizing information processing. Edge-of-chaos computation proposes that maximal computational capability occurs at the boundary between order and chaos. Ordered systems are too rigid for complex computation. Chaotic systems are too unstable for reliable computation. The edge of chaos provides structures that persist yet interact flexibly. Boolean networks, neural networks, and other computational models show maximal complexity and computational power at critical parameter values, separating order from chaos. Boolean networks model gene regulatory networks and other switching systems. Each node has a Boolean state affected by inputs through Boolean functions. Random Boolean networks with k inputs per node show a phase transition at k equals 2. For k less than 2, networks stabilize to fixed points or short cycles, ordered phase. For k greater than 2, networks exhibit chaotic dynamics. At k equals 2, networks show critical behavior with complex dynamics balancing stability and flexibility. The complex domain in parameter space represents regions where complex behavior occurs. Plotting parameters governing system dynamics reveals regions of simple periodic behavior, regions of chaos, and often narrow complex regions between them. The edge of chaos corresponds to boundaries between order and chaos. Evolution might tune organisms toward edge of chaos parameter values because these provide optimal adaptability, balancing robustness against perturbations with flexibility to respond to environmental changes. Fitness landscapes in evolutionary biology exhibit complex topology affecting evolutionary dynamics. Fitness depends on genotype through a complex mapping. Simple landscapes have single peaks. Evolution climbs to the global optimum. Complex landscapes have multiple peaks separated by valleys. Populations can be trapped on suboptimal peaks. Rugged landscapes with many peaks create frustration, where every mutation decreases fitness. Evolution on rugged landscapes might exhibit chaos and complex dynamics. The NK model of fitness landscapes introduces tunable ruggedness. N represents genome length. K represents epistasis, how many other genes affect each gene's contribution to fitness. For k equals 0, fitness contributions are independent, smooth landscape with single peak. For k equals n-1, genes interact with all others, maximally rugged landscape. Intermediate k produces intermediate ruggedness. The NK model reveals how epistasis affects evolutionary dynamics and adaptation. Coevolution produces complex dynamics including red queen dynamics, continual adaptation required to maintain relative fitness as species evolve together. Predator-prey coevolution, host-parasite coevolution, and mutualistic coevolution create frequency-dependent selection where fitness depends on population composition. Coevolutionary dynamics can be periodic, quasi-periodic, or chaotic. Mathematical models show diverse outcomes depending on interaction structure and evolutionary parameters. Economic systems exhibit complex dynamics potentially including chaos. Market prices result from interactions among many agents with diverse strategies and information. Agent-based models simulate economies with heterogeneous interacting agents. These models produce emergent dynamics including boom-bust cycles, bubbles and crashes, and complex irregular fluctuations resembling real economic data. Understanding economic complexity might inform policy and regulation. Social dynamics in networks shows complex contagion and opinion formation. Social influence spreads through networks, with adoption thresholds determining whether innovations or opinions spread widely. Network structure affects dynamics. Clustered networks resist spreading but enable local consensus, while random networks enable rapid spreading but prevent consensus. Coupled dynamics of network structure and social states produces complex co-evolutionary patterns. Traffic flow exhibits complex dynamics including phantom jams. At low density, traffic flows freely. At high density, traffic jams form. In intermediate density, traffic shows complex dynamics. Stop-and-go waves propagate backward through traffic without obvious obstacles. Models treating traffic as particles or fluids capture these dynamics. Understanding traffic flow complexity informs transportation engineering and autonomous vehicle coordination. Ecological networks including food webs show complex topology affecting stability. Early ecological theory suggested complexity destabilizes ecosystems. Modern network analysis reveals that specific network structures, modularity, nestedness, weak interactions, can stabilize complex ecosystems. The relationship between complexity and stability depends on network architecture. Understanding ecological network structure helps predict responses to perturbations, including species extinctions and climate change. Cascading failures in infrastructure networks demonstrate how local perturbations can propagate globally. Power grids, financial systems, and supply chains are coupled networks where failure in one component affects others. Cascading dynamics can amplify local failures into system-wide blackouts or economic crises. Analyzing cascade vulnerability reveals critical components whose failure triggers widespread damage. Designing resilient systems requires understanding cascade dynamics. Phase transitions in complex systems occur when qualitative behavior changes abruptly with parameter variation. Examples include percolation transitions in network connectivity, synchronization transitions in coupled oscillators, and order-disorder transitions in magnetic systems. Critical points separate phases, characterized by power laws and diverging correlation lengths. Understanding phase transitions in complex systems reveals organizing principles and tipping points. Tipping points in climate and ecosystems represent abrupt transitions from gradual parameter changes. Slowly changing conditions might suddenly trigger regime shifts, Amazon rainforest transitioning to savanna, ice sheets collapsing, or ocean circulation changing. These transitions often involve positive feedbacks creating bistability, multiple stable states for the same parameters. Identifying approaching tipping points is crucial but difficult, requiring indicators like critical slowing down and increased variance. Early warning signals might predict approaching tipping points. Near critical transitions, recovery from perturbations slows, critical slowing down. Variance and autocorrelation increase. The system becomes more persistent. These generic indicators appear across systems approaching critical points. Detecting early warning signals could enable intervention before irreversible transitions. However, distinguishing genuine warnings from false alarms requires careful statistical analysis. Emergence describes how macroscopic patterns arise from microscopic interactions without central control. Ant colonies exhibit collective intelligence without any individual ant understanding colony-level behavior. Bird flocks coordinate through local interaction rules without leaders. Economic markets produce prices from decentralized transactions. Emergent phenomena are not reducible to components. The whole exceeds the sum of parts. Understanding emergence requires multi-scale analysis and new conceptual frameworks. Time scales and prediction horizons reveal fundamental limits to forecasting chaotic systems across disciplines. The practical implications of chaos theory center on prediction limits, understanding how far into the future we can reliably forecast chaotic systems. Different systems have different Lyapunov times and prediction horizons, ranging from seconds to millions of years. These limits affect everything from weather forecasting to spacecraft navigation to financial planning, revealing that determinism and predictability are fundamentally different concepts. Weather prediction demonstrates chaos theory's practical impact most dramatically. The atmosphere has a Lyapunov time of approximately 2 to 3 days, meaning that uncertainties double every few days. Starting with typical measurement uncertainties, prediction accuracy degrades rapidly beyond 1 week. By 2 weeks, forecasts retain little skill beyond climatology. This fundamental limit exists despite enormous improvements in observations and computational power. The 2-week barrier reflects atmospheric chaos, not technological limitations. Ensemble forecasting addresses prediction uncertainty by running multiple simulations with slightly different initial conditions. The spread of ensemble members indicates confidence. Narrow spread suggests reliable prediction. Wide spread indicates high uncertainty. Ensemble methods don't extend the fundamental prediction horizon, but quantify uncertainty within it. Modern weather centers run 50 to 100 ensemble members, providing probability distributions rather than single forecasts. Climate prediction differs from weather prediction in targeting statistics rather than specific states. While individual weather patterns remain unpredictable beyond 2 weeks, climate statistics, average temperatures, precipitation patterns, storm frequencies might be predictable decades ahead. However, climate systems can exhibit chaotic transitions between regimes, creating limits to climate prediction. Tipping points represent transitions where predictability breaks down entirely. Ocean dynamics has longer timescales than atmosphere due to water's thermal inertia. Ocean eddies and currents have Lyapunov times of weeks to months. Ocean predictions are useful for weeks to months ahead, longer than weather but still limited. El Niño forecasts can be skillful 6 to 9 months ahead, but accuracy decreases significantly beyond this. Ocean-atmosphere coupling creates complex predictability patterns with different timescales for different variables. Solar system dynamics exhibits chaos over million-year timescales. Planetary orbits are chaotic, with Lyapunov times of 5 to 10 million years for inner planets. This means detailed orbital predictions beyond 5 to 10 million years become unreliable. However, gross features remain predictable. Earth won't be ejected or collide with another planet soon. The distinction between deterministic chaos and statistical predictability applies to celestial mechanics as to climate. Asteroid orbits can have much shorter Lyapunov times, especially for objects in resonances with Jupiter. Some asteroids have Lyapunov times of decades or centuries, making long-term prediction impossible. This complicates assessing asteroid impact risks. Precise prediction beyond several Lyapunov times is impossible. Probability distributions replace deterministic predictions for long-term impact assessment. Spacecraft trajectory design exploits chaos in the three-body problem. Chaotic regions allow dramatic orbital changes with minimal fuel expenditure. Genesis mission used chaotic dynamics to travel from Earth to Sun-Earth L1 point with minimal fuel. Other missions have used lunar flybys and chaotic trajectories for fuel-efficient transfers. Understanding chaos enables rather than prevents these applications. Chaos provides flexibility for trajectory design. Financial markets exhibit complex dynamics with debated predictability. If markets are efficient random walks, prediction is fundamentally impossible. If markets have nonlinear deterministic components, short-term prediction might be possible. High-frequency traders claim predictive ability over seconds to minutes. Long-term market timing remains elusive. Whether financial chaos exists and what prediction limits would apply remains controversial. Earthquake prediction faces fundamental difficulties possibly related to chaos. If earthquake dynamics are chaotic with short Lyapunov times, long-term prediction is impossible. Current earthquake forecasting provides probabilities, likelihood of earthquakes above certain magnitudes in regions over time periods, rather than specific predictions. Whether deterministic earthquake prediction is possible remains debated. Chaos theory suggests fundamental limits may exist. Cardiac dynamics operates at multiple timescales. Individual heartbeats have millisecond timescales. Heart rate variability shows complex fluctuations over minutes to hours. Predicting exact heartbeat timing far in advance is impossible due to chaos. However, statistical properties are predictable. Sudden transitions to pathological rhythms represent critical transitions difficult to predict. Early warning signals might enable intervention before fatal arrhythmias. Neural activity shows complex chaotic dynamics with prediction limits. Exact neural firing patterns are unpredictable beyond milliseconds to seconds. However, neural systems produce reliable outputs despite internal chaos. Motor commands, perceptions, memories show stability. Understanding how reliable computation emerges from chaotic substrate is a major neuroscience question. The brain might exploit chaos for flexibility while maintaining functional stability. Chemical reaction dynamics can be predicted until chaos develops. Simple reactions follow deterministic kinetics, allowing long-term prediction. Complex reactions with feedback can become chaotic. Belousov-Zhabotinsky reaction shows chaotic oscillations with prediction limits of minutes. Industrial chemical reactors must account for potential chaotic dynamics affecting reaction yield and safety. Control systems stabilize desired operation regimes. Ecological population dynamics prediction faces chaos and stochasticity. Simple models suggest chaotic population fluctuations should be common. Natural populations show complex dynamics combining deterministic and random components. Separating chaos from environmental noise is difficult. Population predictions beyond several generations are unreliable. Management decisions must account for uncertainty and potential surprises from nonlinear dynamics. Epidemiological forecasting deals with chaotic disease dynamics. Childhood disease dynamics can be chaotic, making long-term prediction difficult. Vaccination programs alter dynamics, potentially stabilizing or destabilizing. COVID-19 forecasting illustrated prediction challenges, exponential growth, changing behavior, new variants created unpredictable dynamics. Short-term forecasts, weeks, can be skillful, longer-term predictions face fundamental limits from nonlinear dynamics and behavioral responses. Economic forecasting confronts complex dynamics and human behavior. Short-term economic indicators might be predictable weeks to months ahead. Long-term economic forecasts, years ahead, are notoriously unreliable. Whether this reflects chaos, complexity, or fundamental unpredictability of human decisions remains debated. Economic models incorporating nonlinear dynamics and agent-based approaches might improve understanding, if not prediction. Social dynamics, including opinion formation and collective behavior, shows complex temporal patterns. Viral phenomena on social media can grow explosively and unpredictably. Predicting which ideas or products will spread widely is extremely difficult. The dynamics involve coupled human decision-making, creating feedback loops. Small initial differences can produce vastly different outcomes. Sensitivity to initial conditions in social space. Climate tipping points represent prediction limits where gradual forcing produces sudden responses. Ice sheet collapse, rainforest dieback, ocean circulation shutdown might occur abruptly. Predicting exact timing is difficult. Systems might transition in decades or centuries. Identifying approaching tipping points through early warning signals is active research. Uncertainty about tipping points complicates climate risk assessment and policy. Technological forecasting illustrates prediction challenges in complex adaptive systems. Predicting technological development decades ahead is notoriously difficult. Small innovations can have transformative impacts. Path dependence means historical accidents affect outcomes. Technology, society, and policy co-evolve, creating complex feedbacks. Scenario planning acknowledges multiple possible futures rather than single predictions. The fundamental lesson across domains is that prediction horizons exist beyond which deterministic forecasts become meaningless. These horizons vary enormously, seconds for some systems, millions of years for others. Understanding prediction limits helps set realistic expectations and design appropriate strategies. Probabilistic forecasts, adaptive management, resilient design, scenario planning for operating in chaotic world. Philosophical and conceptual implications of chaos theory transform understanding of determinism, causation, and scientific explanation. Chaos theory raises profound philosophical questions about determinism, predictability, causation, reductionism, and the nature of scientific explanation. The discovery that deterministic systems can be unpredictable challenges traditional views inherited from Newtonian mechanics. Understanding these implications helps clarify what science can and cannot do, and what it means to explain and understand natural phenomena. Classical determinism, articulated by Laplace, held that complete knowledge of initial conditions and laws allows predicting the entire future. Laplace imagined a demon with such knowledge could foresee everything. Chaos theory shows this vision is wrong. Even complete knowledge of laws and excellent knowledge of initial conditions cannot overcome exponential error growth. Prediction requires not just laws, but impossibly precise initial conditions. Determinism doesn't imply predictability. This distinction between determinism and predictability is crucial. Chaotic systems are completely deterministic. They follow precise mathematical laws with no randomness, yet their unpredictable, long-term forecasts are impossible. The unpredictability is fundamental, not technological. Better measurements and computers extend prediction horizons but never eliminate limits. Chaos reveals that the universe can be lawful yet unknowable in detail. Free will debates are sometimes connected to chaos and quantum mechanics. Some argue that determinism threatens free will. If the future is determined, how can we have meaningful choice? Chaos shows determinism doesn't imply predictability, possibly leaving room for meaningful agency. However, chaos alone doesn't solve the free will problem. Chaotic systems are still deterministic. Chaos demonstrates that determinism is subtler than once thought. but doesn't resolve fundamental metaphysical questions. Causation in chaotic systems becomes complex. In the butterfly effect, tiny causes have large effects. But does a butterfly flapping its wings actually cause a tornado? In one sense, yes. The tornado might not have occurred without that perturbation. In another sense, no. Countless other perturbations could have produced similar effects. Causal explanations in chaotic systems require statistical or mechanistic rather than deterministic accounts. Identifying the cause becomes problematic. Reductionism faces challenges from chaos. Reductionism holds that understanding components allows understanding systems. For chaotic systems, knowing equations doesn't enable long-term prediction. System behavior emerges from interactions in ways not obvious from components. This doesn't refute reductionism. The equations determine behavior, but shows that reduction doesn't always enable prediction or provide intuitive understanding. Emergence is compatible with reductionism, but adds complexity to scientific explanation. Scientific explanation traditionally involved subsumption under laws plus initial conditions predicting phenomena. Chaotic systems follow laws but resist prediction. What constitutes explanation when prediction fails? One answer is that explanation involves understanding mechanisms and typical behavior rather than predicting details. Knowing a system is chaotic explains why prediction fails. Statistical properties might be predictable when details aren't. Explanation need not require prediction. The role of mathematics in science is highlighted by chaos theory. Chaos was discovered mathematically. Lorenz found it through computer simulation. Mathematical analysis revealed universality. The mathematical structures, fractals, strange attractors, bifurcations, exist objectively in equations before physical manifestation is recognized. Mathematics reveals possibilities that physical intuition misses. The effectiveness of mathematics in science remains mysterious, but chaos exemplifies it strikingly. Probability and chaos interact in interesting ways. Chaotic systems are deterministic, yet behave randomly in some respects. Should we describe them probabilistically or deterministically? In practice, probabilistic descriptions are often useful even though systems are deterministic. Ensemble forecasts treat identical physics probabilistically. The boundary between deterministic and stochastic descriptions becomes blurred, a matter of practical utility rather than sharp distinction. Chaos and quantum mechanics both involve fundamental unpredictability, but for different reasons. Quantum mechanics has intrinsic randomness. Measurement outcomes are probabilistic. Classical chaos is deterministic, but unpredictable due to sensitivity to initial conditions. How these combine in quantum chaos, quantum systems whose classical counterparts are chaotic, remains an active research area. Some quantum properties suppress classical chaos while retaining some signatures. The observer's role in chaotic systems is subtle. Measurement uncertainty fundamentally limits prediction. But chaotic systems exhibit sensitive dependence regardless of observation. The unpredictability is in the systems themselves, not just in our knowledge. This contrasts with quantum mechanics, where observation arguably plays constitutive role. Chaos theory respects classical distinction between observer and observed while revealing knowledge limits. The reality of chaos is sometimes questioned. Is chaos in nature or in models? Real systems have noise, finite precision, and quantum effects absent from idealized models. Strictly speaking, perfect chaos requires infinite precision impossible in physical systems. Yet chaotic models capture real phenomena, whether unpredictability, Hyperion's tumbling, dripping faucets. Chaos is a useful idealization like frictionless planes, not perfectly realized, but capturing essential features. Complexity and chaos are related but distinct. Chaos involves simple systems producing complex behavior through sensitive dependence. Complexity often involves many interacting components. Complex systems can exhibit chaos but need not. Simple chaotic systems show complexity isn't just about number of parts but interaction structure. Complexity science studies both chaotic and non-chaotic complex systems. Ontology of attractors raises questions. Are strange attractors real physical entities or mathematical conveniences? They're never perfectly realized. No physical trajectory exactly traces the mathematical attractor. Yet attractors organize understanding of dissipative systems. They represent equivalence classes of trajectories with shared asymptotic behavior. Attractors have ontological status similar to orbits or energy levels, useful theoretical constructs with empirical manifestations. The nature of time emerges differently in chaotic versus regular systems. Regular systems are predictable forward and backward. Chaotic systems are unpredictable forward due to sensitivity, but differently unpredictable backward. Trying to retroduce history faces similar exponential divergence. Time's arrow isn't explained by chaos alone. Time-reversible chaotic systems are equally unpredictable in both directions. However, combining chaos with other asymmetries might contribute to time's arrow. Beauty and aesthetics in chaos theory are striking. Fractal structures, bifurcation diagrams, and strange attractors have visual appeal transcending utilitarian value. The Mandelbrot set's infinite detail fascinates mathematicians and artists. Whether aesthetic qualities reflect deep truths or human psychology remains debated. Perhaps pattern recognition systems find certain structures appealing, fractal complexity matching natural forms we evolved processing. The limits of science become clearer through chaos. Science seeks understanding and prediction. Chaos shows these can partially separate. We can understand that systems are chaotic without predicting their details. Science can identify prediction limits, itself a form of knowledge. Knowing what we can't know is valuable. Chaos theory expands science by incorporating fundamental limits as part of natural understanding. Cultural and historical context shaped chaos theory's development and reception across scientific disciplines. Chaos theory's emergence in the 1960s through 80s represented a scientific revolution, transforming multiple disciplines and challenging established paradigms. Understanding this history reveals how scientific ideas develop, how resistance to new concepts operates, and how mathematical insights translate to physical understanding. The story involves computer technology, interdisciplinary communication, and changing attitudes toward complexity. Pre-chaos mathematical work laid groundwork unknowingly. Poincaré's late 19th century work on celestial mechanics identified chaotic possibilities but lacked tools to explore fully. Birkhoff continued Poincaré's work in the early 20th century. Cartwright and Littlewood discovered chaotic behavior in forced oscillator equations in the 1940s, but didn't recognize its generality. These early discoveries were isolated rather than recognized as a general phenomenon. The digital computer's development enabled chaos discovery. Lorenz's breakthrough depended on running iterative computer simulations. Pre-computer mathematics focused on analytically solvable problems. Computers allowed exploring nonlinear equations numerically. The accident where Lorenz restarted a simulation with rounded values could only happen with computational tools. Technology thus enabled recognizing phenomena impossible to see analytically. Early chaos researchers worked in relative isolation across disciplines. Lorenz in meteorology, May in ecology, Feigenbaum in physics, each discovered similar phenomena independently. The lack of communication reflected disciplinary boundaries and different terminology. What meteorologists called predictability limits, ecologists called population fluctuations, and physicists called turbulence onset. Recognizing common underlying mathematics required cross-disciplinary dialogue. The term chaos was popularized by James York in 1975 paper, Period 3 Implies Chaos. The term was deliberately chosen for accessibility and provocative quality, contrasting with more technical alternatives. York's work brought wider attention, including popular science coverage. Naming often helps establish fields. Having a term facilitates communication and community building. Interdisciplinary conferences in the 1970s brought together researchers from different fields discovering chaos. These meetings revealed that similar mathematical structures appeared in diverse contexts, whether epidemics, circuits, chemical reactions, celestial mechanics. The universality of roots to chaos and fractal structure suggested deep principles transcending specific applications. Interdisciplinary synthesis transformed chaos from isolated discoveries to coherent theory. Benoit Mandelbrot's work on fractals provided visual and conceptual tools for chaos theory. His 1977 book, The Fractal Geometry of Nature, introduced fractals to broad audiences. Mandelbrot identified fractal patterns in nature, coastlines, trees, clouds, connecting mathematics to visual experience. Computer-generated fractal images fascinated scientists and public. Fractals provided geometric language for describing strange attractors. Popular science books including Glake's Chaos in 1987 brought chaos theory to wider audiences. These works emphasized philosophical implications, determinism without predictability, butterfly effects, complexity from simplicity. Popular treatments sometimes oversimplified or sensationalized, but they created public awareness and attracted researchers to the field. Chaos became part of broader culture, appearing in everything from Jurassic Park to philosophical debates. Resistance to chaos theory came from several quarters. Traditional physicists and mathematicians sometimes dismissed it as overhyped, noting that nonlinear dynamics had long been studied. The popularization bothered some who felt serious science was being trivialized. Others questioned whether real systems exhibit true chaos. Noise and finite precision might wash out idealized chaos. Debates about rigor versus insight, applied versus pure mathematics occurred. Acceptance grew as applications accumulated. Successful predictions of period doubling in fluids, chemical reactions, and circuits validated theory. Engineering applications, including control methods and communications, demonstrated practical utility. As chaos theory matured, it became absorbed into mainstream nonlinear dynamics and complexity science. What once seemed revolutionary became established knowledge, taught in standard courses. Computational tools evolved with chaos theory. Early work used mainframe computers with limited graphics. Personal computers democratized chaos exploration. Anyone could program logistic maps or visualize attractors. Scientific visualization software enabled sophisticated graphics revealing structure. Numerical methods for computing Lyapunov exponents, fractal dimensions, and reconstructing attractors from data became standard tools. computational chaos theory developed alongside physical theory. Experimental chaos emerged as researchers built physical systems exhibiting predicted behavior. Chua's circuit became standard experimental platform. Fluid convection experiments showed predicted bifurcation sequences. Chemical oscillators exhibited chaos. Laser chaos was observed and controlled. These experimental realizations validated theory and provided testbeds for control methods. The interplay between theory, computation, and experiment strengthened the field. Applications across disciplines demonstrate chaos theory's broad impact. Meteorology incorporates chaos in forecast uncertainty estimation. Ecology uses chaos theory in population management. Medicine applies chaos analysis to cardiac dynamics and seizure prediction. Engineering exploits or suppresses chaos in various systems. Economics debates chaotic versus stochastic market dynamics. Neuroscience investigates chaos in brain dynamics. Few theories have penetrated so many fields. Educational impacts include new course offerings and textbooks. Nonlinear dynamics and chaos courses appeared in physics, mathematics, and engineering curricula. Undergraduate courses use chaos to illustrate mathematical concepts and scientific methods. Chaos provides accessible introduction to advanced topics, differential equations, numerical methods, computer programming. Educational software and websites enable exploring chaos interactively. Philosophical discussions about chaos theory engaged broader audiences in scientific thinking. Questions about determinism, prediction, emergence, and reductionism became widely discussed. Chaos theory offered concrete examples for abstract debates. Misapplications and metaphorical extensions occurred. Chaos theory, invoked loosely in social sciences, management, and humanities. Some extensions were productive, others superficial. Distinguishing rigorous applications from metaphorical uses remained important. The future of chaos theory involves integration with other approaches. Chaos connects to complexity science, network theory, and machine learning. Understanding high-dimensional chaos, spatio-temporal chaos, and quantum chaos remain active areas. Applications to new domains including climate tipping points, financial systemic risk, and neural dynamics continue. Chaos theory evolves from revolutionary concept to integrated component of broader complex systems science. If you're still awake somewhere in this exploration of chaos theory, of deterministic unpredictability and sensitive dependence, of strange attractors and fractal basin boundaries, of period doubling cascades and Lyapunov exponents, of controlling chaos and edge of chaos complexity, there's more to contemplate about how simple rules generate infinite intricacy. But if sleep has found you, if consciousness has faded into dreams, rest knowing that chaotic processes continue throughout nature, in your breathing rhythm, in your heartbeat variability, in atmospheric flow outside, in countless systems far from the regular clockwork Newton imagined. While you sleep tonight, your body maintains complex dynamics balancing order and chaos. Your heartbeat shows natural variability, not perfectly regular but not random. This heart rate variability reflects healthy autonomic regulation, with parasympathetic and sympathetic influences creating irregular yet bounded patterns. Loss of heart rate complexity associates with disease and aging. Healthy hearts operate near the edge of chaos, maintaining flexibility to respond to changing demands while avoiding pathological chaos of fibrillation. Your breathing rhythm also shows complex dynamics. Respiratory control involves feedback loops between carbon dioxide levels, brainstem respiratory centers, and mechanical lung properties. Normal breathing is irregular, breath depth and timing vary naturally. During sleep, breathing patterns change across sleep stages. REM sleep shows particularly irregular breathing. These fluctuations reflect complex physiological regulation rather than simple mechanical oscillation. Your neural activity during sleep exhibits complex patterns measurable through EEG. Sleep cycles through stages: light sleep, deep slow-wave sleep, and REM sleep, with characteristic brain wave patterns. Transitions between stages involve complex dynamics. Some researchers propose that sleep architecture reflects self-organized criticality with avalanche-like transitions. The brain during sleep is not simply turned off, but shows intricate spatio-temporal dynamics serving memory consolidation and neural maintenance. Dreams themselves might involve chaotic neural dynamics. REM sleep features rapid eye movements, muscle atonia, and vivid dreams. Brain activity during REM resembles waking in some ways, but with reduced prefrontal constraint. This might allow chaotic exploration of neural state space, random association of memories and sensations, creating dream bizarreness. Some theories propose that dreams help explore possibilities through neural dynamics freed from reality constraints. Your body temperature regulation involves complex feedback. Core temperature varies across the day following circadian rhythms. Temperature drops during sleep, reaching minimum in early morning. This regulation involves multiple interacting systems: hypothalamic control, metabolic heat production, sweating, and vasomotion for heat loss. The interactions create stable yet flexible regulation. Fever involves resetting the thermoregulatory set point through inflammatory signals, another example of complex physiological control. Blood pressure and cerebral blood flow exhibit complex dynamics, including oscillations at multiple frequencies. Very low-frequency oscillations reflect metabolic regulation. Low-frequency oscillations reflect sympathetic activity and baroreflex function. High-frequency oscillations follow respiratory rhythm. These coupled oscillations create complex patterns. Measuring blood pressure or cerebral blood flow shows irregular time series reflecting underlying regulatory complexity. Your immune system operates through complex networks of cell types and signaling molecules. Immune responses must distinguish self from non-self, pathogens from commensals, and threats from harmless antigens. This discrimination emerges from interactions among T cells, B cells, antigen-presenting cells, and cytokines. Immune dynamics can exhibit oscillations, chaos, and complex switching between states. Autoimmune diseases might involve dysfunction in these complex regulatory networks. Hormonal systems exhibit complex temporal patterns, including circadian rhythms and ultradian oscillations. Cortisol follows a circadian rhythm with morning peaks and evening troughs. Growth hormone pulses during deep sleep. Reproductive hormones show cyclic patterns. These rhythms result from interactions among hypothalamus, pituitary, and peripheral glands, creating feedback loops. The coupled oscillators can exhibit complex dynamics, including chaos under certain conditions. Consider how your body exemplifies principles of complex systems, multiple interacting components, nonlinear feedbacks, multi-scale organization, emergent properties. No single controller orchestrates physiology. Instead, local interactions create coordinated behavior through self-organization. Homeostasis emerges from dynamic regulation rather than fixed set points. Your body maintains stability through constant flux. what physiologists call homeodynamics rather than homeostasis. The weather system operating outside your window exemplifies atmospheric chaos. Despite supercomputers and satellite data, forecasts beyond 2 weeks remain unreliable. The atmosphere's sensitive dependence on initial conditions fundamentally limits predictability. Yet within this chaos, patterns persist: seasonal cycles, climate zones, jet streams. Chaos and order coexist, with deterministic dynamics producing apparently random fluctuations while maintaining statistical regularity. Clouds above, if present, display complex structure across scales. Cloud boundaries are fractal with self-similar irregularity from meters to kilometers. Cloud formation involves turbulent convection, microphysical condensation processes, and radiative transfer, nonlinear interactions creating complex spatio-temporal patterns. The same processes creating single clouds create weather systems and climate patterns, illustrating how chaos spans scales from microscopic to global. Ocean currents, driven by wind, temperature, and salinity differences, exhibit complex three-dimensional flow. Turbulent eddies transfer energy across scales. Mesoscale vortices, tens to hundreds of kilometers across, persist for weeks to months. Ocean mixing involves stretching and folding dynamics characteristic of chaos. Tracer particles separate exponentially yet remain bounded. Ocean complexity affects climate, marine ecosystems, and pollutant dispersal. The planet you rest upon has a chaotic orbital evolution over millions of years. Earth's orbit eccentricity, obliquity, and precession vary due to gravitational perturbations from other planets. These variations affect ice ages and climate through Milankovitch cycles. Though approximately periodic, orbital variations show chaotic elements, small perturbations produce long-term unpredictability. Our seemingly stable planetary home participates in the solar system's subtle chaos. Plate tectonics creates complex geological patterns. Convection in Earth's mantle drives surface plates, creating earthquakes, volcanoes, and mountain building. Plate motions and deformation involve nonlinear mechanics and complex feedbacks. Earthquake timing shows irregular patterns consistent with either chaotic dynamics or self-organized criticality. The solid Earth beneath you participates in slow geological chaos operating over millennia. Biological evolution, the process that created you and all life, exhibits complex dynamics potentially including chaos. Fitness landscapes are rugged with multiple peaks. Mutations, selection, drift, and gene flow interact nonlinearly. Coevolution between species creates frequency-dependent selection. Extinction events punctuate evolution. Whether evolution is chaotic or merely complex remains debated, but clearly evolution produces unpredictable outcomes from deterministic processes of inheritance and selection. Your brain, the most complex system known, might harness chaos for computation and cognition. With 86 billion neurons and trillions of synapses, the brain operates far from any simple dynamics. Yet neural networks models and measurements suggest brains operate near criticality, the edge between order and chaos. This might optimize information processing, allowing both stable memory storage and flexible response to novelty. Your thoughts emerging from neural dynamics might involve chaos. The mathematical structure underlying chaos theory, nonlinear differential equations, iterated maps, bifurcations, attractors, represents one of humanity's deepest insights into nature. These equations are not merely human inventions, but descriptions of natural phenomena. The universality of roots to chaos, the appearance of the same mathematical structures across physics, chemistry, biology, and beyond suggests that chaos theory reveals fundamental organizational principles transcending specific systems. The philosophical implications of chaos theory extend beyond science. Determinism without predictability challenges Laplacian determinism, the idea that complete knowledge enables complete prediction. Chaos shows this is false. Even perfect knowledge of laws and excellent knowledge of conditions cannot overcome exponential error growth. This doesn't mean free will exists or that the future is open, but it means the future is unknowable in principle, not merely in practice. Chaos theory also reveals limits of reductionism. Understanding components doesn't guarantee understanding systems. Knowing equations governing pendulum motion doesn't mean we can predict double pendulum behavior far into the future. Emergent complexity arises from interactions. This suggests that complex systems require their own level of description. Reducing to components loses essential features. Chaos theory thus supports holistic and systems thinking. Yet chaos is not randomness. Chaotic systems follow rules. They are deterministic. The apparent randomness reflects our limitations as observers with finite measurement precision and finite computational power. From a hypothetical perspective outside time with infinite precision, chaos would be deterministic and predictable. Chaos thus reveals the gap between mathematical idealization and physical reality, between equations and measurements. The future development of chaos theory will likely involve deeper connections with quantum mechanics, better understanding of high-dimensional and spatio-temporal chaos, applications to biology and neuroscience, and integration with machine learning and artificial intelligence. Open questions remain about turbulence, the onset of chaos in field theories, and whether the universe itself is chaotic. Chaos theory continues evolving as both mathematics and physics. Your relationship to chaos is intimate. You are a complex adaptive system operating near the edge of chaos. Your predictability horizon, how far your future actions can be predicted, is finite. Small choices cascade through your life, creating diverging possibilities. Yet patterns persist. Your habits, personality, values create attractor-like structures channeling behavior. You embody the tension between determinism and uncertainty, pattern and possibility. The peaceful contemplation of chaos might seem paradoxical. How can chaos be peaceful? Perhaps because chaos reveals that unpredictability is natural, not a failure of knowledge, but a fundamental feature of nature. Accepting limits on prediction might free us from illusions of control. The complex beauty of fractals, strange attractors, and emergent patterns offers aesthetic appreciation beyond simple order. Chaos shows that nature is more subtle, more interesting than clockwork mechanisms. See you next time.